Okay, so let's go ahead and get started. So I mentioned to you last time, I made the claim that if it were up to gravity, it would give all objects the same acceleration regardless of what they are, regardless of their mass, their shape. Gravity is very egalitarian. Gravity, if it was up to it, it would give all objects the same acceleration, which is of size 9.8 meters per second squared. That size we often give a abbreviation because it's a number that comes up so often. We call it g. Please note that g is that it's not negative. The negative sign is not baked in to the g. It comes in later when we're setting directions. The direction most generically is downward, but downward being plus or minus is in the eye of the beholder. This is not always true, but it's true near the surface of Earth, which for all everyday situations we're covered. And the thing we have to watch out for is that when we usually observe things flying through the air, we're not really observing gravity acting alone. We're observing gravity and air resistance. So I made the claim that if we could somehow get air resistance out of the picture, then we could really see that gravity treats everything just the same. If we could take air resistance out of the picture, I drop a bowling ball and I drop a feather, they would accelerate together, hit the ground at the same time. It's hard to imagine because we are so used to watching gravity and air resistance act together. So I brought basically the mini version of that demo here. I don't have a vacuum chamber that's big enough to fit a bowling ball, but I do have a miniature version of it. So I have this tube, and standing in for the bowling ball is this red coin. Probably dropped at some point, dropped a coin on the ground and it falls clunk, right, like that. And standing in for a feather, which you normally think of as falling like this, I have these little white scraps of paper, kind of basically confetti, right? So if you throw confetti in the air, you know it kind of goes around like this. But I now have them both inside a vacuum chamber. Those of you that were here before class heard me running the vacuum chamber to get the air out of this tube, or at least enough air so that air resistance could be negligible. So what I'm going to try to do is I'm going to try to let them both drop, and you can see them falling together. So I'm going to put them all in the end here. I have to be careful because they do tend to get stuck, so get them in at the end. And I'm going to quickly tilt the tube, and we can watch them fall across it. Can someone who's sitting there, am I in the, okay. So the question is, when I tilt this vertically, do I go off the end of the video screen or not, hopefully? Oh, some got stuck in the end. Let me try it again. That's pretty good. So, may not be perfect, but you can hopefully see that everything's falling together. Is that in the, can you see that? Okay. So, if anyone wants to is watching this at home either for the first time or doing a review, you can run your YouTube video in slow-mo. If you otherwise it's too fast to see, and you can see everything falling together. Okay? So we're basically watching gravity naked. We're watching what we would observe if you could take air resistance out of the scenario. Okay? And I think one of these trials, the last couple were pretty good, so I'm not going to tempt fate. So now, just to show you there's no trickery, these aren't weighted pieces of confetti or something like that. They really are just everyday confetti. I'm going to let the air back in. Okay, so the normal air had to get back in there. And now we see significant differences in there, right? So gravity really is the great equalizer. It accelerates everything exactly the same. So what we are going to acknowledge is the fact that air resistance is annoying to deal with. We don't want to worry about it. So we're going to have to take a look at scenarios where air resistance is hopefully negligible. So our projectiles are going to have to be rocks and baseballs and things like that that are relatively aerodynamic, where gravity is far dominating their behavior, and air resistance is such a negligible part of what's going on with them that we can neglect it. and hope that our answers are still reasonably accurate. Okay? So what I'm going to do today is just do a bunch of examples, more constant acceleration stuff, with using this as the constant acceleration. So, first of all, just a note about signs. If you choose the positive y direction to be upward, and that's a big if, you don't have to, in your lab, or your free fall lab, which is one of your goals is, of course, to measure this and confirm this, that this is the acceleration given to an object by gravity. But on your lab there, just to not have to deal with negatives, you set a positive to be downward. So then we expect that the acceleration is positive. So here I'm going to choose upward to be positive. That's why the acceleration gets negative. It's not inherently negative. It's negative because I chose positive the other way. So the acceleration is going to be negative 9.8 meters per second squared, or if you can write it minus g. And remember, it has to have the minus in the front because it's not baked into the g itself. Okay? So let's go ahead and just do a quick example. So let me say that I have a building . Those are windows. I'm going to drop a ball off the building. I'm going to basically release it out of my hand. So we drop a ball, and it takes 2.5 seconds to land. And from that, we can deduce how tall is the building. So, very simple example, but it has some subtle points that I do want to make that are useful for other things. So first, let me say I'm going to choose my positive y variable to be like this, or positive y-axis. And then I'm going to, according to my problem-solving strategy, write down my 5 variables in no particular order, and then start filling them in. So if I hold a ball at rest in my hand, like this, and then I release it, what's the velocity now? Well, that's the acceleration. But if I drop something, what's the velocity right at the moment I release it? 0. I drop it from rest. So, however, here's the tricky part. This is one of the side points I want to make that comes up in a lot of problems, and it really prevents students from filling these variables incorrectly. When the ball is in my hand, what's the acceleration right now?
0.
0. Because the velocity is 0, it's at rest, and it's also staying at rest, so it's not changing its velocity. But when moment I release it, its velocity is still 0 because it hasn't had a chance to pick up any speed yet. I haven't given it any time to do that. But now the acceleration is different. That's what's going to pick it up from rest. So it seems like I'm having my cake and eating it too, because I'm allowing the acceleration to change from nothing in my hand to what gravity applies to it, even though I have said that the velocity is still 0. So this is a side point about continuity. And I should mention this is continuity for us in this class. So let's talk about continuity of position, velocity, and acceleration. So first of all, position. Basically, we talked about this as a stand-in for the coordinate. And remember, we're still moving along a straight line. if I want to go, say, from x equals plus 2 to x equals plus 4, okay, I have to go through all the x values in between. I don't have a teleporter, right? If I want to go from this x value to that x value over there, I have to go through all the x values in between. No matter how fast I do it, I have to go through the ones in between. So what we say is that the position for us must be continuous. It can't just change from one value to another. It has to transition between the values in between. We say the same thing about velocity, right? Imagine you're driving along a road at 50 miles an hour, and you want to stop. So you slam on the brakes. You will go through every speed between 50 miles an hour and 0. Now, if you run into a brick wall, you'll do that very quickly, but there will be some point where you are going 40 miles an hour or 30 miles an hour, right? You go through all the velocity values in between, right? So this must be continuous for us. You can't just change from one velocity to another without going through the velocities that are in between them, no matter how quickly. But acceleration, we make an exception. So imagine that same scenario where you're going 50 miles an hour and you want to brake. So it may take you many seconds to slow down. Let's hope you don't hit a brick wall. It may take you many seconds to slow down from 50 miles an hour to 0. But the acceleration, which is what is the guiding that, can change very rapidly. For instance, if you are late for school and your foot is on the gas, your acceleration is forward. But when you realize you have to brake, it might take hopefully only a few milliseconds for you to shift your foot from the gas to the brake. And now your acceleration is pointed behind you. Now, you've gone from that moment, your speedometer says 50 miles an hour and it's increasing because your foot's on the gas, and now you're shifted so that your needle will start going the other way. But of course, just because you've shifted your foot from the gas to the brake doesn't mean you're still not going 50 miles an hour. It's that now it's 50 miles an hour, the needle will stop climbing and go back down, right, on the speedometer. It still takes a few milliseconds for you to shift your foot from the gas to the brake. But of course, as a driver, you should realize that if the acceleration, which is the instructions to the velocity on how to change, just because you've switched those instructions doesn't mean that it won't take time to obey those new instructions, right? So what we're going to say is that that shift with your foot from the gas to the brake being maybe a few milliseconds, we're going to say it's basically instant. So we're going to say that it's okay to be discontinuous. So for us, it's okay for the acceleration to suddenly change from one value to another. And that is exactly what we have going on in our situation. We have that the object was at rest in my hand with a 0 acceleration, meaning the velocity didn't change. And then the moment you release it, the instructions on how the acceleration or how the velocity should proceed is different. Now we're not going to stay at rest anymore because we've suddenly applied a new acceleration. So the acceleration goes from 0 to negative 9.8. However, the velocity, we can say, is still 0. It was 0 on your hand, and it is also 0 at the moment of release because the new acceleration hasn't had any time to do anything to that velocity yet. So we're at the point where we have gone from, say, not having your foot on the gas or the brake, right? We have no acceleration going at 50 miles an hour to suddenly slamming on the gas, okay? So that's what we have. We've switched the instructions for the acceleration, but the velocity hasn't had a chance to change yet, okay? It's okay for this to have a sudden change in value, but the velocity was still going to take time to evolve. Now you might ask, why is it that we allow this? Well, the reason why we allow it is because anytime something can change, we want to describe that. So we talk about change in velocity or change in position with time. We have a quantity for that. Right? We talk about velocity. And it's okay for the velocity to just change in a continuous way because we have a way to talk about that. We have acceleration. But if our acceleration was continuous, we need to describe that. And we don't have that. This is the end of the line for us in this class. You may ask, is there a delta A, delta t, right? Can you talk about changes in acceleration with time? Can you talk about delta A over delta t? Yes, you can. It's called jerk. Acceleration evolving with time. Can you talk about the change in jerk with time? Yes, you can. It's called jolt, and so on and so forth. If you're designing roller coasters or doing elevators or something like that, you need to be worried about this stuff. But we don't worry about it in our class. We don't need to go too far down the line here. So at some point we have to stop. And wherever it is that we stop, wherever is the bottom of the line, well, we have to allow jump cuts in that value because we couldn't talk about the change in that value anyway. All right? So that's what we have here. So that's a little bit of a side on continuity. That's something important to realize, is that the acceleration can change value instantly, whereas the velocity, because we can accurately describe the evolution in velocity, we say the velocity is still 0. Okay? All right. So that's a brief aside on continuity. Are there any questions before I get back to the problem? Okay, so I have 2 things. The third thing I obviously have is 2.5 seconds. It takes 2.5 seconds to land. So, the next thing, I obviously already have the 3 variables, which is the minimum, but I want to talk about the final velocity. So the final velocity, common mistake is to call it 0. The reason to call it 0, people say, well, doesn't it hit the ground and stop? Well, you got to be careful. You've committed to this. That is gravity only. When you have made this commitment, here's what the commitment that you've made. It's after you release it, so you can't be touching it anymore. Remember, when it was sitting in your hand, the acceleration was something else. 0. Or whatever acceleration you want to give it. Okay? When it's touching your hand, the acceleration may not be that. It's important that it has to be, air resistance has to be about 0, because then that's not correct either, right? That is not an accurate reflection of the acceleration if you have a feather that's falling in the atmosphere. And finally, if you've made that commitment that gravity is the only influence, then you can't have other influences like, say, the ground. Okay? So that is also only accurate before you hit the ground. The ground can apply just as many different accelerations as your hand can. It depends. I don't know. What does it hit? Does it land in the mud? Does it land on the concrete? Who knows? So when we say final velocity here, it's not 0. In fact, what that would represent would be the impact velocity before it hit the ground, just before it hit the ground. So your contract, when you're using this acceleration, it's assuming that gravity is the only influence. So you can't have anything else touching it. You can't have a hand touching it. You can't have the ground touching it. You can't have air resistance being significant. So that's really important. What this would actually represent is the final impact speed that gravity could give it just before it hits the ground, and then you no longer know the acceleration. Okay? So make sure you understand why this is not 0. What we're looking for here is displacement. You know that because it's asking how tall, so it's obviously something measured in meters. You go through your problem-solving strategy. You look at equation number 2. Equation number 2 is the one that is missing time. No, that's not right. Which one is missing? Yeah, no, that's right. That's the one that's missing v final. You want to pick the equation that is missing the thing you don't know and don't care about. And I will leave it to you to do the math. And you will find that the displacement is minus 31 meters as it pops out of the equation. Now, it's minus. Is that okay? Can a displacement be minus? Sure. What does that mean? Which way was the displacement? Downward, right? The whole problem is vertically oriented, right? So it was downward. We picked the upward to be positive, so this displacement means you ended up below where you started, right? It just means that you went like this. We should have raised alarm bells if it didn't come out negative, because we certainly were expecting the ball to fall down, and down is negative in our choosing. So what do we put in the WebAssign box? How tall is the building? 31 meters, right? The building can't be negative amount of tall, right? So remember, WebAssign asks how tall, how far, how fast, what is the size of the acceleration, things like that. It always tries to ask it in the way that it's sign neutral. So you should get a sign out of the equation, the sign should have meaning, but you should chop it before you put it in, because I don't want to enforce certain choices for direction that you may not want to make. There would be nothing wrong with working the whole problem with plus being downward. Then this would be plus, and your displacement would come out plus, which essentially means the same thing. Okay, so it means that you went downward. Okay, so that right there, that is this problem. This is a great way to figure out the height of a building. Don't do it with a feather, because if your feather takes much, much longer to fall, it doesn't mean your building is taller. If, for instance, you drop a feather and the wind carries it away and it never lands, the building is not infinity meters tall. Okay? Your whole point of using this value is you've agreed to a very stringent set of circumstances. You've agreed to all of these things. Otherwise, that acceleration is not accurate. Are there any questions on this example before I do another one? Okay, so let's just do another one. Same deal. Just keep doing the same thing, following the same strategy. Example number 2. Let's launch a ball into the air and have it land at the same height that it started. Let me give you some properties of this flight. Let me say that you threw it into the air. You released it out of your hand going 10 meters per second. And here are my questions about this thing. What's the time to the top of the flight? What's the time for the whole flight? What's the final impact speed? All right, so let's start. Now, part A is asking me just how much time does it take to reach the top of the flight? Not the whole flight, just part of it. So here, you should never hesitate to take some subset of the flight. Well, I should say that if you need to, you can take a part of the flight and analyze that. I'll set my initial point at the launch point, my final point at the top, and then the time between them, of course, will be the time it takes to rise to the top of the flight. So let me go ahead and write down my 5 variables in no particular order. I'm going to, again, choose the plus direction to be upward. And if that's the case, my acceleration will be downward, so that's minus 9.8. And my initial velocity would be plus or minus, according to that axis choice. plus, right? I'm launching it upward, so that's the same direction as the positive axis. So what I've basically done is I've given the ball some different acceleration in my hand during the process of throwing it. I've gotten it up to this velocity, and then I let it go. So the velocity that it had in my hand, 10 meters per second, upward, I release it, and now this is still that, because it hasn't had a chance to change, but now the acceleration is this new value, which is going to obviously start immediately taking away from that velocity, right? That's why I'm going to slow down and come back. All right, so there's my two variables. And what's my final velocity at the top of the flight? Zero. So let's compare and contrast. Why can I get away with saying that that final velocity is 0, whereas this is not? Well, the difference is that gravity is the very thing that brought this to a stop. Gravity is not going to be what brings this to a stop, right? If something's falling, gravity will just keep speeding it up forever. Here, if you came to a stop again, it'd be because of the ground, but that's past the regime of validity of your acceleration. Here, it's the very thing, gravity, which is going to stop you. All right, so we have our three things, 1, 2, 3. We're looking for the time. Don't know, don't care about the displacement, although that would be an extremely good problem as well, because that would tell you how high does the thing go, right? That might be something you're perhaps even more interested in. If I throw this thing, how high does it go? But let's focus on the problem at hand. I'm going to pick equation number 1, because equation number 1 does not have displacement. It relates the other 4 variables, the 3 that you have and the 1 that you want. And I'll leave it to you to confirm. Work it out yourself at home. Just do the couple lines of math. And you should find that the time to the top is about 1.02 seconds. A little over a second. Which, by the way, shouldn't be horribly shocking, because remember that the acceleration is going to remove 9.8 meters per second in a single second. Well, that's pretty much what you have, right? You have 10 meters per second to start with. So if you remove 9.8 meters per second in the first second, you barely have anything left. It's going to take a shade over a second to stop completely. Does that make sense? Okay, so we got part A done. Let's do part B. Part B is asking about the whole flight. So one of the ways that I can do it, and the way I recommend, is to just do the whole flight at once. Now you might say, can you do that if you have an up part and a down part, but it's all happening under the same acceleration, so we can go ahead and do that. You can use the equations over as large of a time period as you want, as long as the acceleration is constant, and it is. It's the same acceleration that whole time. It might be instructive to draw the velocity and acceleration vectors. I'll do that in a moment. So let's put down the 5 variables first. What's my initial velocity? Plus 10. The initial point hasn't moved. What's my acceleration? Negative 9.8 the whole time. It's constant. That's what gravity does. The time is what I want, but I do need one more thing, right? I need a minimum of 3. Can I say the final velocity is 0 now?
Yes. Oh.
Can't. Gravity will never stop something while it's falling. That's the ground. That's actually the impact velocity. That's what we're going to find in part C. That's not 0. But you do know the displacement. What's the displacement? Zero. You start and end at the exact same place. Now, that doesn't mean you stayed there. But remember, that's the beauty of displacement. You don't have to care about the details of the trip. You just say, how does where you end differ from where you started? Well, here it doesn't. You start and end at the same place. Displacement 0. All right? So we're good to go. We use equation number 2. Equation number 2 because it's missing the final. So this one has some mild point of interest, so I'm going to show you this one. So this is what it looks like with the y form. Let me plug in what I have, just so I can make a point. 0 plus 10t, 1/2 negative 9.8 t squared. So I have an equation where both a t and a t squared are in there. So this should set off your tingly senses that maybe you have to do the quadratic equation to solve for t. In this case, though, I want to point out that it's not necessary. And the reason why is because you have the great absorber on the left-hand side, a 0. 0 is your friend. And the reason why is you can just divide both sides by t. You'll get rid of this t entirely. You'll get rid of one of these. But you haven't just shuffled your problem over to the other side. Because 0 divided by t is still 0. So you haven't just taken your issue about t and shifted it into the denominator or the other side. So now you get 0 equals plus 10 plus, and then what is that, negative 4.9, and then t. Easy. No quadratic necessary. You shouldn't use the quadratic unless it's necessary because it's time consuming. It's not that it would be wrong, but this is much quicker. The whole flight time is 2.04 seconds. Question?
Since we're not factoring wind or air resistance, when the time it goes up will be the same as the time it goes down?
Yes. So that was the very next point I was going to make, that if you compare these two numbers, you'll notice a trend. And obviously, maybe it's just a coincidence, but if you work it out, you will find that this time would always be twice this time in this particular scenario. So let's talk about that. It took 1.02 seconds to go up. It took apparently 1.02 seconds to go down, and the total flight time was twice that. So this is maybe an opportune time to write down level ground facts. Things that are true when you have a level ground flight. And what I mean by level ground, by the way, don't take that too literally. It's any flight that starts and ends at the same height. You can be standing on unlevel ground, and as long as you're willing to catch it and adjust where your catch is so that it comes out of flight the same height that it went into flight, that's a quote-unquote level ground flight. Okay? So one of the things that's true about level ground flight is that the time to go up to the top and the time to fall back is equal. So let me try to motivate why that's the case. This is where I'm going to draw my vectors and show you a little bit about the general progress of the velocity and acceleration. So my velocity is initially upward. I guess I'll draw that in red. But when you release the object from your throw, the acceleration due to gravity is downward. So I guess I'll draw that in green. So very first thing that's going to happen, of course, is that velocity is going to start getting reduced because the acceleration works against it. So if we draw it, say, right here, we can draw the velocity vector has gotten much smaller. You're slowing down, but acceleration of gravity is relentless. It's still there, same as ever. And so what's going to happen now is you're going to slow down some more. And in fact, by the time you get to the top of the flight, what's your velocity? 0. So your velocity is 0. Is your acceleration 0 too? No. What would happen if the acceleration was 0 there too? Just hang out there. That doesn't happen. The acceleration is relentless. The acceleration says, hey, don't get too comfortable there. The only reason you're stopped is because I finished slowing you down and I'm about to start speeding you up. from here, it proceeds exactly like this. So what we're about to write down is basically what happens in this problem. You start from rest, and the acceleration that gravity applies is now going to turn your velocity around. If you apply a negative acceleration against a positive velocity long enough, you'll slow it down, stop it, and make it turn to your own side. Okay, so now the acceleration is now the acceleration has always been negative, but now the velocity is negative too. And so now you're going to speed up, and by the time you get to the bottom, the velocity has increased even more under the guise of the acceleration, which is acting the same way. So it's no wonder that the time to go up and the time to go down are the same, because it's all happening completely symmetrically with the same acceleration guiding the whole motion. The only difference between going up and going down is that while you're on your way up, you're slowing down, and when you fall, you're speeding up. The only difference is that the velocity and acceleration are opposite on this side and in the same direction on this side, but everything else is completely symmetric. So of course, it takes just as long to slow down to a stop as then to speed up, and to give away the punchline, you're going to end up with the same velocity by the time you get to the bottom. You'll be going 10 meters per second, but in the negative direction. And I'll show you that momentarily when I knock out part C. Everything is very symmetric. And it's because it's all happening under the same exact acceleration that's guiding the whole thing. The only difference is that when you're going against that acceleration, you'll slow down, and when you're going with it, you'll speed up. So level ground flights are extremely symmetric for that reason. Okay, so I have any questions on that before I just knock out part C and prove to you that the final velocity is also 10 meters per second, but in the downward direction? Okay, so that's a little bit about the times. And those of you that have seen this before, perhaps your instinct would have been, if I asked you just for the total flight time, your instinct might have been to just find the time to the top and multiply by 2. I call that the multiply by 2 crowd. And they get way too accustomed to doing things assuming that symmetry is always in place. The next and final example I'm going to do is what I call an unlevel ground flight, where you start and end at different heights. Then the multiply by 2 crowd gets really lost. Okay? I want to point out that I got this answer without having to take this and multiply by 2. I got this from scratch. I got this from scratch by using the initial velocity, the acceleration, and the fact that the displacement happened to be 0, but maybe when the displacement's not 0, I just put it in, and I solve anyway. So level ground is a nice symmetric thing to look at, but it shouldn't be the only thing you can do. So let me knock out part C, and then we'll do just that. I'll show you an unlevel ground flight. That's the last option. As far as the setup goes, it's the same setup as part B, because it's also a property about the final impact speed, so it's still a whole flight question. Same 3 givens, 1, 2, 3. It's just I'm asking for this, right? So it's the same setup, which I guess I'll recopy. So part C, same setup, initial, final, same 5 variables. Same knowns, 1, 2, 3. The only difference is that I'm now solving for this, and I don't know and don't care about this. Now you might say, well, I know it's 2.04 seconds. I just did that. Why can't I use that? You can. But maybe you want to do part C first. I don't know. Maybe you don't trust your answer from part B, and you don't want it to tank your answer for part C. You can do every single one of these parts independently. None of them are contingent on the answers from the other. In this one, we do equation number 3. And again, there's a little bit of a hitch in this equation, so I do want to show you real quick. how it proceeds. So if we go ahead and plug it in, we have plus 10 squared, 2 times negative 9.8 times 0. Well, the fact that that displacement is 0 really means that this whole second part is irrelevant, right? Anytime the displacement is 0, you basically are going to get v final squared equals v initial squared. Here's where you have to be careful. If the squares of two numbers are equal, does that mean that the numbers themselves are equal?
No.
No.
We call them a negative.
Exactly. There's a 1 and a negative 1 are not equal, but their squares are equal. So this is, by the way, equation number 3 has the singular distinction of all 5 equations that it has some vector quantity that's squared. It has a v, both v initial and v final are squared. So you have to be careful when you're square rooting, which is it? V final could be plus or minus v initial. This is something uniquely in equation 3 you have to watch out for if you're solving for one of those. When you take the square root, you have to make some intelligent decision. And by the way, the math is not going to help, right? The math tells you it's either plus or minus. You have to use your physical intuition, your common sense. Should the final velocity be upward or downward? Downward. So negative. Opposite to the direction of the initial velocity, which was positive. So that sign is chosen not because the math tells me that, it's because common sense tells me that. And by the way, you can see that that will happen anytime the displacement is 0. It's going to be added here to my level ground facts. V final is the opposite to V initial. Same speed, opposite direction. It's just another consequence of the extreme symmetry of going up and coming down. Same acceleration guides the whole process. The same acceleration will take that launch velocity, shrink it to 0, and then add all of that launch velocity back in the same time and the same distance. Okay? So the launch speed is the exact same amount. If we were asked for speed, of course, in WebAssign we would type in 10 meters per second because speed is not the same as velocity. Speed is the size of the velocity. All right? So that's something where basically if you have an aerodynamic projectile, it will impact at the exact same speed it was thrown. This is why it's not, for instance, a good idea to fire bullets into the air, because if they hit somebody, then it will go basically almost as fast as when it was shot. Now that's not quite the case because of air resistance, which is significant for a bullet because it's going so fast, but generally don't shoot your guns in the air, okay? It's not a good idea. There have been people killed by being hit by bullets that were fired straight into the air and they just had a high enough impact speed. Okay, so that's this example, example number 2. Again, giving you a little bit of a spin around how to work the equations, giving you some idea of the symmetry of level ground flights. But we should be accustomed to the possibility that maybe something doesn't always land at the same level that it's launched from. So let me do a quick sketch of one of those. So this is my third and final example. My third and final example, I'm going to launch something off a cliff. I'll launch it upward at a speed of 5 meters per second. But I'm going to assume that when it comes back down to the same level, I've yanked my hand out so that it's going to continue to fall, and it's going to fall all the way down. So let's say that it ends up dropping through a height overall of 30 meters. So the process proceeds much the same way. So I don't want to belabor any, I don't want to do like a triple part example, ABC example. I just want to show you what's the tricky part. The tricky part would be to find the time of the whole flight. So let me go ahead and do it. I can do it all in one fell swoop. The initial velocity is here, or sorry, the initial point is here, the final point is down here. I don't need to split it up into parts because the entire flight is guided by the same acceleration, so I can do it all at once. Let's put down the 5 variables in no particular order. The entire flight is guided by the same acceleration, which is going to be negative if I choose upward to be positive, which I will, just like I have done in the previous examples. You might at some point pick at least one of these examples, rework the whole thing with downward being positive, and make sure that that doesn't ruin your whole world, okay? And it will emphasize that there's no universal plus and minus. What's my initial velocity? Plus 5, right? It's upward. I'm looking for the time, so I need at least one more thing. Can I say my final velocity is 0 down here? No. Something would never come to a stop because of gravity. That's, in fact, the impact speed, impact velocity. So, I can say what's the displacement? Negative 30, that's right. You wind up 30 meters below where you started, and downward is negative. So you connect an arrow from where you started to where you ended, and that is downward. And downward, in this case, is notated as negative. Now you might say, well, didn't it go up first and then come back down? Yeah, the distance traveled is way more than 30 meters. But the beauty of these equations is they'll take care of it. How does it know to take care of it? Well, if you start with an upward velocity, but then wind up below where you started, it knows what happened. It means that you take this positive velocity and you apply this acceleration for a pretty long time, it knows you're going to stop, turn around, speed up, pass your initial height, and keep going. It's all the information it needs is in here. So remember, the displacement is, again, to emphasize homework number 1, is just the difference between where you started and where you ended. Who cares what happened in between? It doesn't matter. All right, so let's do it. We are led once again to equation number 2, based on V final, which is missing. And again, because there's something of note in the equations, I'm going to do it out for you. So let's go ahead and put in the things. I would normally encourage you to solve symbolically, but here I want to show you what happens. If you put in these numbers, negative, or half times negative 9.8, negative 4.9. So you get this equation for t. Now I want to compare and contrast that with before when we had level ground, right? We had displacement being 0, and the 0 was that great absorber that allowed us to divide out a t. That will not work anymore. If you try to divide out a t here, you'll just put your t in the denominator of the other side. There's no way to solve this just by manipulation for t. You have to use the quadratic equation. So you manipulate it into the right form by putting in all the terms to one side. Don't forget that step. You have to have 0 on the other side. You identify your coefficients, a, b, and c. And then you put it into the quadratic. Okay, so the answer t equals negative b plus or minus square root of b squared minus 4ac all over 2a. Now you don't have to memorize that. It is available on the equation sheet. So first of all, we should probably address how it is that we got into this bind. You don't want to use the quadratic equation needlessly because it's time consuming. When do you need to use this? When do you need to use the quadratic equation? It comes up very seldom. Equation number 2, I guess, or equation number 5, are the only equations that have a variable both squared and not squared. So that's when you have to watch out for it. and the variable in both of those, which is squared or not squared, and not squared, is t. So that's, of course, exactly what we ran into. We're using equation number 2 with time. Even then, you could avoid it. Look at this, right? We had used equation number 2. We had to solve for time. We got away with not having to do it because of that 0. So the displacement not being 0 is another reason why we have to use the quadratic. There's even one more out you have, right? If the initial velocity is 0, then this kills this term. So you just solve for t squared and then square root it. So the initial has to not be 0. There's a lot that has to go wrong, quote unquote, before you are forced into this. And that's exactly what you should be looking at on the setup. You go, oh, equation number 2. Oh, time. Will one of these please be 0? No. Okay? So we are forced in the quadratic equation. I will leave it to you to show that the 2 roots that come out, of course there will always be 2, are 3 seconds and minus 2. Okay, well, the ball does not go backward in time. The positive root's the answer, the negative answer you throw away. The answer for the flight time is 3 seconds. So if you do it correctly, you should always get 1 positive answer, that's correct. 1 negative answer you throw away. If you get 2 positives, you did something wrong. If you get 2 negatives, you did something wrong. And for those, let me just make one more point here. The negative root is not complete garbage. What it represents is that if you go back in time, down here, you could also get to a displacement by going backwards in time by 2 seconds. So it's actually useful sometimes to realize that, yeah, this 3 seconds should take longer than this 2 seconds. In fact, looking at these two, the entire arc that we're looking at would take 5 seconds. So this would be 2.5 seconds, and this would be 2.5 seconds. We've just split the arc up asymmetrically, so the part that goes forward in time is 3 seconds, and the part that happened in the past, if you had imagined the ball being launched from the ground, that would be 2 seconds. So it's not complete garbage. It is sometimes useful. Okay, that's it for today.